So I'm going to be going over data pipelines. I've got in the repo some examples using TensorFlow and PyTorch, and I'll focus on the TensorFlow example at the moment. We'll go through building the pipelines. The idea here is that on modern systems with accelerators, you've got an accelerator doing the heavy computation, like processing your model in the forward and the backward pass. And then you have a data pipeline running on the CPU side, on the host side, where the you can be doing data manipulation, augmentation, loading your data in real time, shipping that off to the accelerator. And so you want to make sure you're utilizing those two resources in parallel and not blocking or underutilizing the host machine. So I will share my screen. And I will make things bigger as we go. Keep things arranged here. There we go. So we'll be using Slack for help in the background. People will be on there while I'm going through this. So we will be down in O2 data pipelines. And so we'll be using the ImageNet data set for this example. And ImageNet it's very commonly used benchmarking data set for image classification, semantic segmentation, those sorts of things in machine learning. And there are some, I point you at the examples on the TensorFlow website here, but we'll go through the example that I have in the repo. And we'll just dive right in. So I have these two directories, one for TensorFlow, one for PyTorch. I have submit scripts. So these you would run on the command line, either on Theta GPU or on Theta KNL with this call. So you need your project, in this case, SDL workshop, and the queue, which is training dash KNL or data training dash GPU. And these are set up so that all your log files end up in the log file or the log directory. And I also have, in the case of the TensorFlow version, I use, or I have the TensorFlow Profiler set up, and the TensorFlow Profiler will be covered in a later session. So I won't go into the details there. I'll just use it as a way for us to visualize how the workflow is working. So I have a serial version and sort of the standard version that you would always want to use. And then I have all my configuration info in a JSON file. So this sets things like the batch size, our shuffle buffer, and we'll go through these, what they mean, how many parallel readers we're going to have, the number of classes in the data set. In this case, it's 1,000, the number of input channels. These are JPEGs, so they have RGB color, 3 channels. And then how I'm sourcing my data. And you can see here where our ImageNet data lives on Theta in case you want to do some of your own testing. And then essentially I have a file list on the in a text file here. It's just a list of all the files that I'm going to use for training, and then a list for all the files that I'm going to use for validation. And I'll show you how we use those in the data set here. Make sure this is big enough for you guys to see, since I'm using my secondary monitor. So let's start down here at the top level. So down here is where we start at the beginning, pass in our configuration file. You can set your log directory here, and some simple settings like the number of steps. And then TensorFlow uses these interop and intra-op parallelism for defining how the operations, and this is for the CPU side, how the CPU side operations are going to be parallelized. And you can see where those get set right here and here. Then we have, so I'm doing this with the profiler, with the TensorFlow Profiler. So I'm putting that there. I'm telling it where to log the information. And then I call get datasets, and this returns my train dataset handle and my test dataset handle. So we'll look at that function up here. Okay. And so I'm passing in the config, which is a parsing of it's just the dictionary that came in from the JSON file. And here I'm defining the crop size. This tells me how big my image is going to be. And then I am reading in the train file list and the test file list from that configuration JSON file, making sure that those exist. And then I am I'm parsing the classes from these. So this is a function that uses class labels from the file names. So the file names include some string that essentially identifies what it's coming from. And then I convert those into a unique class ID. And then we can build our data sets. So we'll focus on this. I'm not going to focus on how I'm parsing the data in this case, because this is ImageNet. This is very specific to ImageNet, whereas this is the part that we're interested in. So this is just a function that takes our configuration, takes the file list that we care about, and returns the dataset handle that then later gets returned from this function. So let's focus on build dataset from file list. Okay, so that's what this is. This is literally just a list of all the full paths to our input files. So, and then we've got some configuration info. This is the config data. This, you might recall, has the batch size information and how we're going to parse some of our data. I also check whether or not we're using Horovot. This would be the same, the important thing here is that if you are doing parallelism, you want to make sure that you're handling your data intelligently. And when you do distributed training, you don't want to be, or you don't necessarily need to have every rank process all the data. You can have each rank process a different piece of the full data set. When you have a big data set, that's the route you tend to want to go, because that's why you're distributing it. And so we're going to use the information about the ranks that we have to decide on which subset the process will train on, so that it's not training on the same as other processes on other nodes. So here we're going to load in our file list. So I just open up those file lists, and then I'm going to loop over and I'm going to build out. I'm just going to read each line. Each line is one file name. And so now I have my file list. I'm going to calculate how many batches per rank I have so that I can report out, how many batches I'm going to be processing. And now I start using the TensorFlow dataset utilities to build my iterable dataset that TensorFlow can use for its model. So here I'm creating a data set which takes a tensor and essentially just creates a tensor object that's a tensor of strings in this case. So these are a tensor with all of my file names in them. Now, if I'm using Horovod, I'm going to shard this file list based on how many ranks I have in total in my MPI infrastructure and what rank am I. So this is going to be used by TensorFlow to make sure that every MPI rank gets a different set of batches to train on, so that every rank, so that none of the batches are repeated, essentially. So, and then I'm also going to perform a shuffle, which requires essentially a shuffle buffer size to say how big of a memory block I'm going to use for shuffling. So it will, if I use a really small buffer, it's going to read in, say I have a buffer size of 10 and my batch size is 2. It's going to read in 10 images, the next 10 images, and it's going to shuffle them randomly. And then I'm going to batch those, and then it'll do it again as we go. So we want to make sure that that shuffle size is quite large. I think I had it set to 10 or 100,000 in comparison to our data set size. Obviously, it eats away at our memory, but this is happening on the CPU side, so it's less of an issue. And then this is the important thing. So this is really where we're converting our file names. So up to this point, all of our operations have happened just on a list of files that correspond to the JPEGs that we're going to process. This map function applies this function to every entry in our tensor. So in this case, this function will take each file name and convert it to the actual image. And then I can also do this with parallel calls. So this is going to parallelize this operation, and it does it. I let TensorFlow decide how this should be parallelized, how much parallelization should happen here. So I'm going to get back a bunch of JPEGs now in this data set, and then I'm going to unbatch these. This just essentially does a NumPy flatten, and now I'm going to tell it how to batch those images. And then I'm also going to say that it should prefetch some number of batches ahead of time, and I'm going to let TensorFlow do that. And so that just means that this essentially keeps the CPU busy, this prefetching. So otherwise, if I do the prefetching, what TensorFlow will do is it will get one batch, and then that batch goes to the model on the GPU. And it's going to wait until I ask for the next batch, and then it's going to do it again. That means I'm going to be sitting, my GPU is going to be sitting, waiting for all these operations to happen. With the prefetch, it's going to automatically prefetch some number of batches, even if the GPU is busy. So that again allows our CPU to maintain some busy activity while the GPU is busy processing our forward and backward passes. So now let's look at this function. So this is the load image. So this is where some of the more messy details of how we're parsing our data, how we're doing any data augmentation might happen. So here you can see the function takes an image, the path to our image. And then I do some parsing. I'm trying to also load up some of the annotations, which tells me some truth information about the image, like the class information, what's contained in the image, so that I can use it for training. Then I use some TensorFlow built-ins like the IO read file. So this is just going to read the JPEG. Now I have a tensor object, I'm not sure if it's actually a tensor object at this point, but it's some binary data, I suppose. And then I pass that to this decoded JPEG, which is going to decode the JPEG and create the tensor with the 3 input channels. So this image should be the size of the cropping that I passed in at some point. I'm trying to remember where I passed that in, with 3 channels, which actually I tell it how many channels are in the image right there. And then I also expand the dimensions here so that I can get a batch index in the front. Here's the cropping. Okay. Convert it to float 16 in this example. Convert it to other types as you like. I do my resizing to get it to the crop size. And then I get the truth information. And here you can see I'm returning the image and the label. And I don't think I'm using the bounding boxes in this example, but I left it in here just in case for the ImageNet processing, because ImageNet comes with bounding boxes information if you want to train that sort of model, like a YOLO style model. Okay, so every time we call this mapping function, this JPEG is being processed, the label, the truth information from the annotations are being processed. Oh yeah, I am using bounding boxes then. Because I think in this case, what I'm actually doing is I'm using the bounding boxes to cut out the class object. So I have 1 class per image to really simplify this down to a classification problem, not a bounding box problem. So right, and so the important thing here is to always think about how are we parallelizing our workflow. We want to make sure that everywhere we can, we're letting the CPU keep busy and keep building out our data pipeline so that our GPU is not constantly waiting for the next batch. And so we went through this. I think we can now run through some examples. Are there any questions? Yes, I can go full screen. And I can make that bigger. Sorry, I didn't do that sooner. Okay. So now we will go through an example. Let me first bring out, let's look at a submit script for Theta GPU. So here you can see we're setting up our Conda environment where our Python modules are installed. As usual, we need to find out how many nodes we're running on. In these cases, I'm always just going to use 1 node. And ranks per node, calculating total number of ranks. You can set the OMP num threads for the CPU side. What kind of parallelism do you want on the CPU side? And in this case, I just set it to 64. I think if you're using the single GPU queue, which I'm not sure in this tutorial we are, I think this is limited to 32, because OpenMP will check and make sure that you have, it will limit you based on how many threads are reported in the proc CPU info. And then we're just going to call Python because I'm not doing any MPI in this example. On Theta GPU, if we were doing MPI, obviously there would be an MPI run with some number of ranks here and ranks per node. And I'm going to do this twice. I have the parallel example here, and then I have the serial example here, just so you can see the difference in the runtime. And then I also set the number of interrupts and interops. And again, I'm using the log directory for all of my log files just to keep things organized. And as you'll see, it also makes it easier for let's see, will be right. Is it here? Yes. Okay, so I'm on Theta GPU, and I'm down in my TensorFlow dataset API. And I'm just going to run qsub -a SDL workshop. I think it's training GPU, and then the submit Theta GPU. Okay, I think that's actually going to take a full node. Okay, that. And now, like we said, you'll see your log stuff down here. Okay. So if I look at the job ID, so if I grab this job ID, and then I'm just going to do a quick less of job ID and then the error. Okay, so here we see our output as it's looping over. You see a batch number, input shape, label shape, and I print off the labels. These would be the class labels of the objects. And the output is where all the bash is ending up. And sorry for those. Ignore the connection timeout messages. Those are coming from the port forwarding that I'm doing for the profile output. So once this finishes.
Taylor, could you increase your font size a bit? It's a bit hard to read.
Yep. Is that better? Better?
Yeah, that's better. Thanks.
Okay. Yes, please feel free to speak up. Okay, so I think that is exited. So that was job number 9, 10. So I'm just going to bring up the TensorFlow profiling, and I have some instructions in my README for how to view this, but there is going to be a profiling session tomorrow where they'll go into detail on how to look at these. So essentially, I'm running a browser on my laptop that I'm port forwarding to Theta so that I can see the data that's sitting there. Now, when you first, so we're looking at this profiling in TensorBoard. I have the parallel version here. I'm going to go to this trace viewer, which shows, here, let me make this bigger. Unfortunately, I don't think I'm going to be able to make the text in here any bigger. Zoom. Yeah, I'm not sure if, okay, it's doing something, I guess. Okay, so when you bring up this viewer, you have runtime up here at the top. and you have different kinds of processes. You can see the GPU stuff up here, but I'm not running any model training in this example, so you're not going to see anything useful up here. And then you have all the CPU stuff happening down here. I'm not sure if I can continue to make this any bigger. I feel like it's just making this sidebar giant. But we can zoom in over here. And we can see some of our, let me see if I can make this more visible, because the zooming is being annoying right now. So I'm going to put this back to where it was, and I'm going to just share my browser to see if I can make this clearer, because it'll look more. Okay, let's stick with that. Okay, so let me go back to the full view. Okay, so when you look at this, you're going to see, and you'll see this tomorrow, you'll see a bunch of stuff in the front. Sorry, my puppy is getting anxious. You'll see all this stuff in the front. This is all initialization for TensorFlow. And then as soon as everything is set up, the data pipeline will go into operation. And so what you'll see, and we can look at this slice here and see where the activity is lined up on this edge. I've added a 1 second delay in the training loop to sort of simulate the training loop on the GPU. So the GPU is busy for a second, effectively, before the next batch gets called. And so what you see is essentially in the beginning, because we have the prefetch set up, a couple of batches are built, and then what we can see in our view here is that everything else gets lined up on these edges. So every time a batch is fetched, a new batch is being pre-fetched for the next time it's needed. And then the CPU is relatively idle otherwise. So I mean, we still have some compute capability left here. And of course, it's a little deceiving as well. It's a little deceiving as well because I'm only doing one thread here, or one MPI process effectively, and on a Theta GPU node, you'd at least be running 8. So this would be competing with 8 other MPI processes that are trying to build batches at the same time. But it gets the point across. And see, when you zoom in here, you can start to see, like, here's the read file happening in different threads in parallel. They're reading the JPEG. And then you also see the eager pi function. So this is my custom file, or the custom function that was in the map call. It converts reads the JPEG, reads the annotation file, builds the image, builds the truth, and processes those images. And let's see what this stuff is in here. Yeah, you can see some of the conversion to tensor taking place. So there's various operations that are represented down here in these calls based on what my eager Python function is doing to convert the JPEG. But the point is, you can see these all line up. So these, as I go through these rows, each row is a different thread, and they're all processing events. And you can see there's many, many threads being called, and they're all processing the batch in parallel. Now, I also, in that same call, I did this serial one, And you can see the dash serial is where I store that information. So we'll go down to the trace viewer and look at this again. Okay. And here you can see, I think it's still using a thread pool of 8 because I believe it still has that auto set. So TensorFlow is still doing a little bit of parallelism, but you can see there's quite a bit more activity in each of these threads. And one train step here at the top, so this is one of my training loops, is requiring between 18 and a half, or no, this is about 19 seconds to 21 and a half seconds. So it's even longer than what my parallel version was taken, even though I inserted that 1 second sleep. And so if we continue to zoom in here, you'll see similar activities taking place as was in my other in the other function, or in the other example, except for they're condensed down to a couple of threads. So you can see the read file taking place. There's the decode JPEG right there. There's a crop and resize, the cast, resize. So the point here is you don't want the loading of your data to be the bottleneck. So you want to make sure you're taking advantage of these data pipelines that allow you to parallelize the reading and the writing, or the reading and the training. I also did these on theta, KNL. I'll show that quickly. So yeah, so the shuffle is changing the order of the images. And would it help to shuffle after the load? It wouldn't help to shuffle after the load because your shuffle buffer would have to be bigger. Well, I guess it depends on what size of images. Maybe if you're dealing with MNIST or whatnot, maybe it's not as big as a string of characters. But you consider if all I have to do is shuffle a bunch of file paths that are strings of, say, 50 times 8-bit characters, or if I have to shuffle a bunch of 1,000 by 1,000 by 3 images, the amount of memory that you need for that buffer is bigger. So that's why I did the shuffle on the file names instead of the images. But I mean, you can do either one. So, okay, so this was the theta example. So again, here's theta. Again, I have 64 parallel threads reading and parsing files, and you can see these nicely delineated buffer, essentially where the batches are being built. So one batch is being built here, another batch is being built here, and then my training loop again has a 1 second sleep statement. And this is on, again, on the theta KNL. So here you can see this is, maybe you can't quite read that, 30 seconds is right here. This is 32 seconds. So you can see the 1 second delay between the two calls. Now, if I go to the serial version, lots of cool information in this data, in this profiler, especially on the GPU. So tune back in tomorrow for that. session. And then this is the serial. And so you can see there's one serial thread here that's dealing with your data, building of a batch. And you can see it's now taking, here's 45 seconds. So this is about 47 seconds. And that goes past 56, so almost 10 seconds to build a single batch. Oops, I clicked something. Yeah, come back. There we go. So you can see it's quite long compared to, so this is, again, 10 seconds to create one batch versus a fraction of a second in the parallel version, which I showed back here. Yeah, there you go. So in this example, these two lines here represent 1 second in duration. So you can see within a half, less than a half a second, the full batch is constructed. So that is, and let me just point out that this is also, there is a equivalent example in PyTorch, where you'll see very much similar behaviors. Let me move back to this other screen share. Okay. I'm just going to shrink this to make it more. Okay. So if I come back here and now I switch over to PyTorch, very similar structure. Again, same setup, different framework. In the case of Torch, in case of PyTorch, you end up creating a class, a dataset class for your dataset, and you just have to create some specific functionality. The idea is that this object is iterable, so you need standard Python iterative interface where you've got a get item function and a length function, just like you would in a list. And I have a bunch of helper functions that are similar to the ones that I have in TensorFlow, like the read JPEG, where I'm parsing the annotations, cropping based on the bounding boxes, getting the labels, returning those objects. I have a crop and resize. And then I have a class method that's from file list, so that essentially just creates so when I go down to get data sets, so it's the same kind of function that I had in the beginning on the TensorFlow example, where you pass in your configuration and it essentially creates a data set from each of the file list configurations and returns those. So then my main looks very similar. I guess probably the one big difference in the TensorFlow and the Torch case is the Torch case has they delineate a data sample, a data set, which essentially represents the data, how to access the data. And then there's a data sampler object. And the sampler defines how you iterate over the data set. And in this case, I'm using a distributed sampler, just like in the, let me bring up the torch or the TensorFlow just to give you a side by side. So in the TensorFlow example, I was ensuring that MPI ranks processed different batches by sharding the data into pieces. And I told the shard function how many ranks I had and what rank am I. So if I look at the Tensor or the PyTorch example, I do the same thing, but in this case, I'm telling the distributed sampler that information, not the data set. So in this case, I pass the data set. I tell it how many ranks I've got in my system and which rank number am I. I tell it whether or not I want it to shuffle on epoch boundaries. I also tell it to drop the last batch because I haven't made sure that my data set is precisely n batches long. So to avoid any weird things where I might end up with one image in my last batch, which breaks your batch normalization layers or any of that stuff, I just tell the sampler to ignore the last batch in the data set. And so I do that twice, once with the train and once with the test. And then I have a data loader. Sorry, it's actually the data loader that I'm going to iterate over. And the data loader has my data set. It does the sampler, has the sampler. And I can tell it to do things in parallel. So it'll use the sampler to sample from the data set, and it will do it in parallel for however number of parallel readers I define in my configuration file. And I think it's set to 8. And then it takes the batch size. I tell it to keep the workers alive instead of spawning them every single time it needs a data. If you don't set this, it spawns a new thread every time you need a batch. And so that just makes it faster if you just keep the threads alive. And now I can iterate. So I have a simulated epoch loop, and then I'm going to loop over my training data set. So I can enumerate that loader, the train loader, extract my inputs and my labels, print those to screen, and continue. Okay, so these are very similar. The torch is a little different because of the way they've added these additional, essentially extracted out some of the logic that Torch is doing in the back end for you. In general, this is a good thing. Not only does it give you a little more flexibility in how you control your data pipeline, but it also helps you see what's happening, whereas TensorFlow is trying to obfuscate that from you. There are times where that obfuscation will get in your way and you don't know that's the problem because you weren't aware of what it was doing in the back end. So, okay. And then you can run these in a similar fashion. Just use your Q subs for the proper system, and then look for the log files down in the log directory. Okay, are there any questions? I did it this way. I mean, there are certainly simpler ways to make your data pipeline. And I think, right, I mean, I wanted to use the image net data set because it was too big to fit in memory. And more often than not, the tutorials you get online are all things that just easily fit in memory, like MNIST and Ceph-R10. They can just all be loaded on any modern system, and you don't have to deal with anything in real time or any thought process. And most scientific data sets are not that small, especially if you need many nodes to train your your model on, you're going to be dealing with this fact that you can't fit all of your data in memory. So I think the only additional complication that you could get from beyond this is if you wanted to load fraction, if you wanted to run enough parallel nodes, enough parallel MPI ranks where you could fit the entire data set in the aggregate of memory that you possess, and then use MPI to push batches around to your ranks. I didn't implement that here, but that certainly has been implemented before, and is a good way to overcome file system limitations, right? I mean, if you have 1,000 ranks all trying to read these files at the same time, you're going to start seeing some slowdowns, and it may become your bottleneck. And if that's the case, you do want to push everything into RAM, and then use your high-speed interconnects to push the data around from node to node, because the interconnect has higher bandwidth than the file system. So if you find yourself in that situation, just be aware that there is an additional step that you can take to reduce the processing time on the batch preparation side. So, any questions?
Yeah, Taylor, in the PyTorch example,